লাইটগুলো নিভিয়ে দেবো, সাদা লাইটগুলো আমার চোখে লাগছে, এত পাওয়ারফুল পুরো গরম হয়ে যাচ্ছে। বন্ধ করে দিই।
Hello.
Okay.
Hello. Good evening, Siddharth. Where have you been?
Hello.
Where you have been? Home. Hello. Siddharth. Priyanshu.
Hello. Yes, sir.
Hello. Where you have been?
Sir, village.
Home.
Yes, sir.
Priyanshu, have you seen the video? Did you get the video last class?
Hello.
Siddharth, did you get the video last class?
No, sir.
No, sir means he didn't send you. Priyanshu, video नहीं भेजा आप लोग का?
नो सर, नहीं सर, नहीं मिला, नहीं भेजा सर।
रिया शॉर, रिया श्रीवास्तव, अंजलि, सिद्धार्थ, प्रियांशु। देखते हैं ठहर, अभी देखते हैं। एक सेकंड। फोन तो करो। Riya Srivastav, where you had been? Riya Srivastav,
यस सर।
last class where you had been?
सर तबीयत ठीक नहीं था सर लास्ट क्लास में।
क्या हो गया था बेटे?
सर हेड बहुत पेन कर रहा था।
सिद्धार्थ,
हाँ
भी ठीक है?
हाँ सर वो ठीक है।
I have sent that particular video long back. जिस दिन क्लास हुआ था नेक्स्ट दिन भेज दिया था.
सर नहीं मिला सर, वो आया हुआ है बस व्हाइट बोर्ड वाला।
हाँ,
यस सर वो मतलब उन्होंने आगे में फॉरवर्ड नहीं करी सर।
उस दिन ही भेज दिया था मैंने. Was trying to call him actually.
ओके।
Because last class was especially important actually. Structure से तो क्वेश्चन आएंगे. And I explained everything about structure. चल, let's start today. We are going to look into molecular orbital theory. This is the last part of our discussion of the. और एक छोटा part है dipole moment बस. Then we are going to start with gas laws. This is called molecular orbital theory. अरे আগের দিন তোমাকে দুটো ভিডিও পাঠিয়েছিলাম, পাঠাওনি? হ্যাঁ, বহুদিন আগে বললাম যে the students wanted it বলে পাঠিয়েছিলাম আমি. Kindly send it to them. ঠিক ঠিক, কারণ ওই অনেকগুলো ছেলে ক্লাস করেনি তো আমি সেজন্য পাঠিয়ে দিয়েছিলাম. চল. So what we are going to do today is we are going to talk about molecular orbital theory. Up to what, how much we have done till now. First of all, we did the Lewis dot structure, how to basically talk about the bondings and all. First one, what we did was Lewis dot structure. The second thing what we did was essentially the valence bond theory, where the concept of hybridization takes place. We talked about the valence bond theory. The third one, what we did was in the last class, essentially, said the last two classes, essentially, we did VSEPR theory, right? Today, what we are going to do is we are going to do molecular orbital theory. In short, we call it as MOT, that is molecular orbital theory. And upon completion of this, we'll complete chapter 4, right? Except dipole moment portion is still remaining, which we are going to do continue in the next class. And then of course, we are going to start also with the gas laws. So from next class, we are going to do the gas laws part. Right. And you can expect a question paper this week itself. The question paper will be on atomic structure, periodic table, and chemical bonding. So this week, most likely there will be a question paper in which you need to give an examination at your home, not at man. No, we are not going to waste time by me sitting down out here while you people are giving examination. There's nothing of that sort. I'm going to send you the question paper. I mean, Joyanto is going to send you the question paper. You need to answer them and bring it, return back the answer scripts to us. Right. Chal. So we are going to talk about molecular orbital.
Sir, on which day?
Most likely I'll be sending the question paper by Saturday. So you have to look after that. So any day I'll give you a couple of days time, right? So you answer those.
Okay, sir.
Right. So we are going to talk about molecular orbital theory. Now, as the name suggests, is this that essentially we are going to consider molecules out here. We are going to consider what? We are going to consider molecules out here, right? Now, previously what we did, if you remember, we said, say for example, I have got methane. Say, for example, I had got methane previously. And while we talked about the kind of bonding in methane, what did we do actually? We said that, just a moment, Raki, eta ki bondo kora jabe na? So we have got methane. In methane, what we did was this. I'm sorry for the disturbance. There's a lot of cooking going on. So as far as methane is concerned, I have got carbon out here. Now, when I have got carbon out here, Then I said the electronic configuration of carbon was 1s2, 2s2, 2p2. And we said that the valence orbital only takes part into reaction in chemical bonding. So my valence shell is this. So this is 2s and this is 2p. And then we said was this, that all these 4 atomic orbitals actually combine to give you sp3 hybrid orbitals. We said this while we talked about the bonding of methane, hybrid orbitals. We talked about this in the last class and the second and the previous last class. Right? What you are combining out here, that's the most important part, that when you are talking about the difference between valence bond theory and molecular orbital theory. In valence bond theory, essentially you were combining combination of atomic orbitals was there. Combination of atomic orbitals of the same atom was there. That means essentially this S belongs to carbon. All these 3p orbitals also belong to carbon. And you have combined all these atomic orbitals together. That means what you get in the end result is nothing but a mixture of atomic orbitals of the same atom. That is something that you need to understand. You are getting hybrid orbitals, which are nothing but the combination of atomic orbitals of the same atom. That means what you get out here, these hybrid orbitals, has got character of atoms, atomic orbitals, character of atomic orbitals. That means atomic orbitals essentially retain the character of atomic orbitals, even though you mix about S and P. This was what we talked about, the valence bond theory. Hybridization, the concept of hybridization. But in molecular orbital, you are going to do something completely different. You essentially say, for example, you have got a hydrogen out here. In this hydrogen, you have got the electron in 1s. You take another hydrogen out here. Also, it has got an electron of 1s. Now, what you are going to do is this. You are going to combine the atomic orbitals of this hydrogen with the atomic orbital of this hydrogen to create what we call as the molecular orbital. This is a fundamental difference. So what you are doing out here, combining orbitals of 2 different atoms which are getting bonded to each other. Essentially, 1 hydrogen plus 1 hydrogen gives you what? A hydrogen. And what is hydrogen? Hydrogen is nothing but a molecule. So you are combining 1 orbital of hydrogen with another 1s orbital of the second hydrogen to create a molecular orbital in which both these 2 electrons are there. And you call this combination of this atomic orbital with this atomic orbital as the molecular orbital because it belongs to this particular molecule. It no longer belongs to 1 atom. It no longer belongs to the second atom. But this particular orbital essentially belongs to hydrogen. And that's why you call it as molecular orbital, because you create a molecular orbital. Out here it was what? Out here it was, okay, I have got 4 sp3 hybrid orbitals. So carbon has got 4 sp3 hybrid orbitals. So one is like this. The second one is like this. The third one is like this. And the fourth one is like this. So I've combined this S and P3 of the same carbon. And all the orbitals that I'm producing are nothing but essentially atomic orbitals. And then this 4 hydrogen atom comes, sits down out here. So it was essentially the combination of only atomic orbitals, and all the characters of atomic orbitals are retained. But out here, no. The atomic orbitals are combining together to create a molecular orbital. This is a fundamental difference between molecular orbital theory and the valence bond theory. And you can be 100% sure that some questions will obviously come from molecular orbital theory, especially the application part, not the theory part. But without theory, you cannot understand the application also. So let me ask you, all of you, did you understand, Priyangshu? Riya, did you understand? Riya Srivastav? Riya Shah?
Yes, sir.
Riya Shah?
सर
हाँ बोल बेटा.
सर समझने की कोशिश कर रहे सर सर लास्ट क्लास तो अटेंड नहीं किए थे, वीडियो तो अभी आया था तो वीडियो भी नहीं देखे थे.
ठीक है, लास्ट क्लास के साथ आज का कोई रिश्ता नहीं है. हाँ ठीक है, लेकिन ये पार्ट समझे, ये पार्ट तो समझ में नहीं आएगा, छोड़ो बेटा, लेकिन ये पार्ट समझ में आ. यहाँ पर क्या कर रहे हैं हम लोग? हाइड्रोजन के एक इलेक्ट्रॉन कहाँ पर है बेटा? 1s ऑर्बिटल में.
हाँ सर.
ये वाला जो हाइड्रोजन एटम है, इसका इलेक्ट्रॉन कहाँ पर है? 1s ऑर्बिटल में. ये दोनों 1s ऑर्बिटल का इलेक्ट्रॉन are combining together with one another to give a molecular orbital. That means no longer the atomic orbital character is there, it is now a molecular orbital. Because दोनों हाइड्रोजन कंबाइन करके मुझे क्या करता है? हाइड्रोजन मॉलिक्यूल बनाता है. They combine together to form hydrogen molecule. तो इसको जब ऑर्बिटल रहेंगे, इसको दिस कंबाइंड एंटिटी मॉलिक्यूल का, इसको हम लोग बोलते हैं मॉलिक्यूलर ऑर्बिटल. रिया शाह, डिड यू अंडरस्टैंड?
Yes, sir.
अंजलि?
Yes, sir.
प्रियांशु?
Yes, sir.
Fine. I think Diman has lost connection. Chalo. So this is what is molecular orbital. Now I'm going to explain how this is happening. Chalo. This सब गड़बड़ हो गया. I started with the wrong page. Anyway, let me give you the theory of molecular orbital. छोटा सा theory है, nothing much. Theory of molecular orbital. Look. Suppose I have got atom A and I have got atom B, right? I've got these two atoms. Suppose the electron of atom A belongs to psi A. This is the atomic orbital of A. Suppose the electron of B stays in psi B. This is the atomic orbital of B. Right? So I have got psi A and I have got psi B. What is psi A? Atomic orbital of A, in which the electron is staying. What is psi B? Is the atomic orbital of B, in which the electron of B is staying. Now, what we are going to do is this. We are going to do LCAO. We are going to do what? We are going to do LCAO. What is LCAO? Nothing but is a short form, is an abbreviated form of what? Linear combination of atomic orbitals. So linear combination of atomic orbitals is what we are doing. So L for linear, C for C, combination for C, A for atomic, O for orbital. So we are going to basically add these two things together. That means we are going to basically add this psi A and psi B. That means we are going to add, linearly add. What do you mean by non-linear addition? Suppose I added like this, psi A plus psi B whole square. So this is non-linear addition because both of them are not linear. This is linear combination. That means I'm going to straightforward add these two things. Mind it, this is not algebraic addition. Psi is what? Psi is a wave function. What is this? This is nothing but a wave function. Remember atomic structure. What is psi B? That is another wave function. So we are going to add these two wave functions. Right? Fine. Now, how we do this is like this. Together, when they basically combine or add together, they form essentially by linearly combining these atomic orbitals. What they essentially form is they essentially form a molecular orbital called as psi AB. And mathematically, we can write this as psi AB is equal to N, which I'm going to explain what is this all about. CA psi A plus CB psi B. What is N? N is a constant, which is called as normalization constant. What is CA and CB? CA and CB are other two constants, two more constants. If the molecules are same, same, that means both A and B are hydrogen, then CA and CB will be equal to each other. If these two molecules are different, say for example NH3, then I've got two different kinds of atom, and under that condition CA and CB will be different. What does this normalization constant actually gives you? This normalization constant actually ensures that our electron is in three-dimensional space. Our electron, that means only one electron has to be there. Right? CA and CB means what? These are two more constants. What does it do? To minimize the energy. Not required much. I'm just explaining. Minimize the energy. So essentially what I've done is this. I've added linearly psi A and psi B, and these three are constant, which is a mathematical requirement to ensure certain things. That the orbital has got minimum energy, number one, and number two, to ensure that the electron is there in a three-dimensional space. Right. Now, psi AB itself doesn't have got any meaning. As I told you long back when we discussed about atomic structure, the wave function itself doesn't have got any meaning. You have to extract meaning from that wave function. So in order to find out the probability of finding out the particle, what did we do? Suppose this was my wave function. What did we do to find out the probability? We said that, okay, psi A whole square. This gives you what? The probability of finding out the electron. So out here, if I want to find out the probability of an electron, right, between A and B means where within A and B is there, what I need to do? I need to basically square it. So I squared it. So this thing also has to be squared. Now, when you square this, n square becomes 1, right? So forget about that. What it becomes is this CA whole square psi A square plus 2 CA psi A CB psi B plus CB whole square psi B whole square. This kind of expression actually comes out. Right? Now, I've just basically squared it, right? And I did nothing, A plus B whole square, I did nothing more than that. Simple. The meanings are important, however. What does this mean? This essentially gives you is a psi A square. That means the probability of finding the electron upon this A. That means whether the electron is going to stay, or what is the probability of finding that electron around A. What is psi B square? Psi B square essentially says the probability of finding out the electron at B. So if the electron stays around A, there'll be no bond. The electron has to be in middle. Only then it can be shared by A as well as B. But if the electron is staying only around A, there's no bond formation. Similarly, if the electron is around B, there's no bond formation because A is not getting any part of that electron. So psi CA psi A square and CB psi B square essentially says the probability of finding out the electron either on A or B depending upon which term you are actually considering. If these values are high, it means no bond formation. But if you go to this, what does it mean? I can write this as CACB psi A psi B. I can write this in this particular fashion. I have written the same thing. I just arranged the constants in one particular club, and that's psi A psi B out here. This is the most important part. This is the most important part. What it does says is, it says about the probability of finding out the electron between A and B. So what does this thing? This basically gives you the probability of finding out the electron between A and B. And you give a special name to this. You call this as overlap integral. Higher the value of this particular term means the probability of finding out the electrons at the middle of A and B is higher. It means bond formation is there. So essentially, amongst all these three terms, the most important term out here is this overlap integral, which essentially says you what? It essentially says you the probability of finding out the electron between A and B. That means the electron is getting shared between A and B. That means a bond formation is there. That is the meaning of this particular term. So this is of vital significance. Not required though when we basically solve problems, but I'm just giving you a theory in case one or two short questions comes from here. Right, very good. Now, so I have got the probability. Now let's talk about the overlap integral a little bit in details. What I said essentially that I have got psi A. What does it mean? It means the electron, it is the wave function of the electron around A. What is psi B? Psi B is the wave function of the electron around B. Right? What did you do? You essentially added, forgetting about the constant, psi A plus psi B. So you have added two different wave functions. Not a mathematical algebraic addition. It's a wave function addition. Okay, fine. I'll explain it in details. Suppose my psi A looks like this. Suppose my psi A looks like this. Right? Psi A looks like this. So psi A looks like this. I'm just drawing only one complete wave. I'm not continuing with the waves. So this is what? This is my psi A, the white color. It's a wave. Right? I call this as minus and I call this as plus. What does this plus and minus sign says? It doesn't have the algebraic meaning. It only says when it is plus sign, the amplitude goes on increasing in the positive direction. What does this minus sign actually means? It means that the amplitude goes on increasing, however, on the negative side. So plus and minus essentially talks to you about which direction the wave is moving. Nothing more than that. Not an algebraic plus and minus. So this, say for example, this white color is my psi A. Suppose I take this as psi B, the color of psi B is this. And suppose I consider this as hydrogen and I consider this also as hydrogen. Now, all the wave functions of same atoms, say for example, hydrogen. Hydrogen I can collect it from here in my home. I can collect it from Priyanshu's home. I can collect it from Ria's home. Really doesn't matter. Hydrogen is hydrogen. And therefore, the wave function of hydrogens will always be the same. 1s ka hydrogen ka orbital will always be the same. Right? Now, suppose this wave function goes directly on top of this line, directly on top of this line. The same line which is repeating, same line. That means we say that both psi A and psi B are in phase. So what I'm going to do, now the white one was my psi A, the green one is my psi B. Both of them are actually going to the highest position at the same time, going to 0 at the same time, going to the negative highest position at the same time, coming back to 0 at the same time. So there will be what we call as constructive interference. If you remember, we talked about this while we talked about waves. So there will be constructive interference. Now, if there is constructive interference, then the amplitude of the white color and the amplitude of the green color, that means both these functions are going to add up with one another. So this will be doubled. So this will be, so this will be doubled. So this will be doubled. The same phase will be maintained, the same phase will be maintained. Everything will remain the same. This will once again be plus, this will be once again my minus. So that means I am having a constructive interference and both of them are in the same phase. Right. Now what does this actually mean? It actually means this was my psi. So if I make it as psi square, that means the probability of finding out the electrons at this particular position or this particular position becomes the highest. That means the probability of getting the electron at this particular place and this particular place is the highest because you need to do multiply. So multiply minus sign essentially becomes plus. So this is called what we call as constructive interference. How can we reflect this in our pictorial diagrams? Understanding through waves is okay. But how to basically represent it in pictorial diagrams? Now, what do we know? We say, look out here, we say that this is, say, for example, my one of the s orbitals. Right? And say, for example, this is my another s orbital. Another s orbital. Now, both of them are positive. That means both of them have got the same phase. Whereas both of them are increasing in the same way, decreasing in the same way, coming to 0 at the same time. Everything is the same. So both of them, say, for example, are positive. That means I'm mixing one positive with another positive. Under these circumstances, what is going to happen? Under these circumstances, this was my nucleus. This was my nucleus out here for this atom. This was my nucleus for the second atom. And out here, this particular area, they are converging, which is nothing but the overlap integral. This is nothing but my overlap integral. And out here, they are going to add together each other. If they're going to add with each other once again, then how is they going to basically look like when once they combine? Essentially, they are going to look like this. I have got this axis. I have got this axis. And they are adding with one another. This is, say, for example, my nucleus, one of the nucleus. This is my second nucleus. They're adding with one another. At the middle, that means the probability of finding out the electron at the middle of the nucleus is the maximum. Therefore, the curve is going to look like this. The curve is going to look like this. At the middle, you have got the maximum overlap. At the middle, you have got the maximum overlap. This is how the curve is going to look like. So what I did, I basically combined one S. Both of them are in the plus sign. That means they are rising and falling in the same way. I have combined one s orbital with another s orbital. Together I have added them. and came to a combination, linear combination of these two atomic orbitals to give rise to a molecular orbital, which have got a shape like this because they are adding. At the middle, this will be the maximum. So if you look at it at the middle of the axis, the maximum amplitude is there. That means the probability of finding out the electron is maximum at the middle. Therefore, a bond formation is there. We call this orbital as a bonding orbital. Is it clear to all of you? Yes or no? If you don't understand, please ask me. Priyanshu, yes or no? Riya
Sir,
Srivastava?
please explain it again.
Yeah, Riya Srivastava?
यस सर।
समझ में आया ना? समझ में नहीं आया बेटा?
सर वो लंबा वाला जो बताया ना कर्व हो जाता है उसमें थोड़ा प्रॉब्लम है।
लंबा वाला अच्छा यहाँ पर ये वाला?
नहीं नहीं सर, ये ग्रीन वाला।
ये अच्छा ग्रीन वाला, ठीक है। रिया शाह, एनी प्रॉब्लम्स बेटा?
यस सर।
अंजलि?
सर ये ग्रीन वाला।
हाँ ठीक है, ठीक है, देखते हैं। अंजलि?
हाँ सर।
कहाँ पर दिक्कत है बेटा?
सर थोड़ा सा,
कहाँ पर है
सर
बेटा?
थोड़ा सा वो,
कहाँ पर है बेटा?
सर सर बाउंडिंग ऑर्बिटल जहाँ पे आप लिखे हैं वहीं पे सर थोड़ा बता दीजिएगा, रिपीट कर।
ठीक है, ठीक है, ठीक है। सिद्धार्थ, where is your problem? Where is what is the problem in your life? सिद्धार्थ?
सर दोबारा बता दो, डिस्कनेक्ट हो गया था।
Yeah. Did you understand this and this portion? I have got two orbitals, two waves, which are running parallel to with one another. I am considering oneness of hydrogen with oneness of hydrogen and combining them in such a way that both of them are actually rising and falling in the same manner, in unison with one another. Up to this much, everybody have understood? That means what happens? For the green one, my amplitude was this. This was my amplitude. For the white one, my amplitude was also this. So what will be the total amplitude? The total amplitude will be the green plus the white. So this was my green and this is my white. So total amplitude will be this much. That means what? The psi value is maximum at this point and this point. If the psi value is maximum at this point and this point, that would naturally mean that psi square will also be the maximum at this point and this point. That means what does psi square actually means? Probability. That is probability of finding out the electron at this point and this point is the maximum. Is it clear? Just show me your hands up. Up to this much, is everything clear? Up to this much, yes, yeah. Priyanshu says yes. Riya says yes. Anjali says, Riya Shaw says yes. Anjali समझ में आया अभी तक?
यस सर।
हाथ तो दिखा बेटा, देख. Now, what can I do is like this. What can I do out here is like this. This is, say, for example, I have got two orbitals out here, pictorially. So this is my oneness orbital. The white color, right? White color oneness was there. That means it is going in the plus direction. Let me put in this particular thing as plus. This is initially rising in the plus direction. So let me write this as plus. Let me just write it down, plus. The green color is also basically going to the same path as the white one. So I have got another orbital out here. Both of them are hydrogen oneness, and this is also plus because they are following the same path. Yes or no? Up to this much, yes or no?
Yes, sir.
Now what's happening? Look out here. I'm adding this thing. What I'm doing is this, I'm adding this thing. That means what I'm doing is this, I'm adding this white one with the green one. So I'm adding both of them. क्या हो गया? Amplitude ज्यादा हो गया ना? कहां पर? जहां पर amplitude maximum है. That is, when I add this, essentially what I am doing is this, I am bringing these two atoms close to one another. This is my 1s, and this is also my 1s. I'm bringing them together. Yes or no?
Yes. Sir.
That means, yahan par, out here, when I'm looking in this particular place, when I'm looking at this particular place, there is no overlap out here between this green, and there's no area which is common. But out here, what's happening? This is also, say, for example, increasing. This is also increasing. The same way it is increasing. That means out here, the amplitude will be maximum. This is my nucleus. This is also my second nucleus. So at the middle of them, they are converging. If they're converging at the middle, that means the amplitude out here will be maximum at the middle. And at the side where there is no overlap, it will be same. So won't my this two combination will give this curve? Just consider this curve with this one. This is also plus. This is also plus. Out here, there are two pluses. So won't there be a much higher value between this?
Yes, sir.
Who says yes? Priyanshu says yes, right? What about Riya Srivastav, Riya Shaw, Anjali, Siddharth, and
Yes, sir.
Yes, sir.
Siddharth?
Yes, sir. Yes, sir.
You call this just because you have got right now the highest electron density at the middle of between the middle of the two nucleus. That means there is a bond formation because the electrons have come between the two nucleuses. Therefore, you call this as the bonding orbital. Therefore, you call this as the bonding orbital. Now, suppose instead of bonding orbital, what you do next is, थोड़ा सा ये जब लेक्चर देखेंगे ना, थोड़ा सा उल्टा सीधा हो गया आज पेज. I started with the wrong page. So एक बार देख लेना 1 2 3 करते, मैं कर दूं 1 2 3 करते better. This was my, not this one. We started with this, right? So this is page 1. This is page 1. This is page 2. And this is page 3. And from page 4 onwards, it will be continued. Page 4. So after page 4, everything is okay. Right. Now, suppose now I have got this kind of an orbital now. That means one is plus, the other one is minus. Say, for example, the other one is minus. The other one is minus. That means while this is increasing in this particular way, right? The green colored one, this is one wave. This is one wave function of one hydrogen 1s. The other hydrogen 1s moves just in the opposite direction. Like this. Right? Now this white color, I'll call this as plus. White color, I'll call this as plus. So it at the beginning, it is going in the plus direction. That's why I've said plus. The green color at the beginning is going in the opposite direction. Therefore, what I'm going to say this, I'll call this as negative. Now, look out. Out here, my amplitude was this. Out here, the amplitude isn't this. The amplitude in both the cases are the same. But one is going in the positive direction. One is going in the positive direction. The other one is going in the negative direction. Therefore, they are going to nullify each other. Together, they will make 0. Jitna upar utha, utna niche na plus and minus make 0. When this kind of curve actually comes out here, we call it as destructive interference. We call this as destructive interference. Right? Fine. Now, destructive interference. That means here per the probability of finding out at the electron at the out here will be 0, because out here they are completely negative. Out here also they will be equal, but in opposite direction. So throughout, between the two nucleuses, there will be no electrons. They're completely nullifying each other. So you call this as a destructive interference. Now, the same diagram, right? I'm going to draw it in circle spheres. So this is my, say, for example, my one particular hydrogen 1s. Now, I have got the nucleus out here. The other one, the same sphere, right? The same thing I've got out here. Now, this one is minus. Now, this one, say, for example, is minus. One is plus. If one is plus, the other one is minus. So, I call this as minus. Right? This is the nucleus, and this is minus sign, and this is the nucleus, and this is plus sign. Now what I'm going to do this, I'm going to basically bring them to overlap each other. Chalo, overlap karate hain. So this is my one orbital, one hydrogen. This is my other hydrogen. And I'm overlapping them one another. This was my plus. This was my plus, and this one my minus. This was my nucleus. This is my second nucleus. So my nucleus is out here. This is one nucleus. This one is the second nucleus. Right? Now see, whenever they're interfering with each other, whenever they are coming in together with each other, they're making 0, because they're completely nullifying this and this. That means when I combine this together, linearly, when I'm combining them linearly, mind it, this is all linear combinations. So what kind of curve we are going to get? This is, let's say, for example, the axis of my nucleus, these two nucleuses, right? This is my, say, for example, my one nucleus, and this is my second nucleus. I'm combining them together, but out here is a destructive interference. That means there'll be, this particular portion will totally vanish, because this minus is going to eat the plus out here, and this plus is going to eat the minus out here. So in between, I'll be having no electrons. So it will be like this. I'll be having like this. This will be my, oh, sorry. This will be my minus. This will be, say, for example, this will be minus outside. So this I'll call it as, this was plus, so I'll call this as plus. Because in between they have eaten each other. Similarly out here, as far as the negative sign is concerned, it will be like this. Out here is minus, so out here it will be minus. Minus. So in between these two nucleus, there is absolutely no electron. Psi becomes 0 in between the nucleus. So there is no bonding formation out there. There will be anti-bonding. That means when I'm combining the two orbitals, I can combine like this, psi A plus psi B, or I can combine as psi A plus of minus psi B. This will give rise to a bonding orbital. And when I'm combining this, it will give rise to an anti-bonding orbital. Right? Now, bonding orbital, why does at all atom bonds? The atom essentially forms a bond because of the simple reason that they lower their energy. That means bonding orbital will be having lower energy than either of the individual atoms. And anti-bonding orbital will be having higher energy than any of the individual atoms. So if I want to draw a graph, say for example, I have got one hydrogen out here, A. I'm just writing down as A, and I'm writing down here as B. Okay, fine. No, I'll not write down A and B. I'm going to write down as one hydrogen 1s for atom A. I'm considering atom hydrogen. I have got the second atom hydrogen out here, for it is also 1s. When the two plus signs are basically going in phase with one another, in parallel to one another, in phase, then they are going to form bonding orbital. So the energy will be lowered. And when they are basically going in opposite phase with one another, an anti-bonding orbital is going to get formed. So we represent this in this particular diagram. So this is what is called as my bonding orbital. And this is what we call as anti-bonding orbital. Right? So how much did the energy actually for the bonding orbitals has decreased? This was my individual energy for each of the single 1s hydrogen. So the energy has decreased by delta. And for here, the energy has increased by delta, because both of them has to be same, because energy can neither be created nor be destroyed. Together, if I take this energy to be 0, then if the energy has decreased by this much for this orbital, the energy has to increase by this much for the other one. Only then the summation of these two energies will be coming to this 0 part. So this is a bonding orbital and this is the anti-bonding orbital. And we represent the bonding orbital by just calling them sigma, if it's a sigma bond, or pi. We represent the bonding orbitals either as sigma or as pi. We'll understand a little bit later. But as far as anti-bonding orbital, we represent them as sigma star, which star as actually means anti-bonding, or pi star. देखो समझ में कुछ आया क्या नहीं है? एक बार सोच लो. Now I'm going to actually start into the real part. Right now I'm just giving you the theory of what's happening, why, what is bonding, what is anti-bonding, stabilization. Now I'm going to start actually the real part. अभी तक तो मैं तो खाली just give you the introduction part. See whether you've understood this or not. Just go through it, see whether you've understood or not, and then only you ask me. I'll give you a couple of minutes. Also, let me take a break for 2 minutes. Coming right away. Any problem anywhere? Any one of you? Priyanshu,
Yes, sir.
clear up to this point?
Yes, sir.
Riya Shah,
Yes, sir.
Anjali beta,
Yes, sir.
Riya Srivastav and Siddharth.
Yes, sir.
Siddharth.
Yes, sir.
Right, chal. Now we are going to start. So let's start. Now look, the fun of, I'll show you a small application right away, and then I'm going to explain the details, right? Chal. Let's start this. What's happening out here is like this. As I told you, I have got a hydrogen 1s out here, and I have got a hydrogen 1s out. So this is one atom and this is one atom. I'm combining them linearly with one another. Two combinations is possible. One combination is the constructive interference. That means both the plus signs are together. That means in between the two nucleuses, the maximum concentration of electrons will be there. Therefore, it will be bonding orbital, right? So out here, I'll be having a bonding orbital out here, right? And bonding orbitals, as I told you, is referred as sigma. So I'll call it as sigma. What kind of orbitals they are mixing with one another? 1s and 1s. Therefore, I am going to say the molecular orbital is sigma 1x, because 1s is mixing with 1s atomic orbital is mixing with 1s atomic orbital of atom A and atom B. Right? Then it can also be like this, that they go for destructive interference. That means one is plus, the other one is minus. In this case, between the two electrons with nucleuses, there will be absolutely no electrons. That means there's no bonding at all. In fact, it is anti-bonding. So this will be of higher energy. So this is my higher energy anti-bonding orbital. And I call this as sigma 1s star, because they're forming a sigma bond. Sigma bond means what? If I remember, I told you head-to-head collision. That means I have got a head out here and I have got another head out here. Two of them are colliding with each other. Head-to-head collisions is taking place. And that's why you call this a sigma bonds. Pi bond is like this. Pi bond is like this. You have got this and this, right? So they are not directly actually colliding with each other. They are basically sitting down and parallel to each other. This is my axis of the nucleus. So there's no direct to direct collisions. You call this as pi bond. So, but this is my sigma head-to-head collisions. Sigma bonds can only have, sigma orbitals can only have head-to-head collisions. There's no question of lateral overlap. So this is sigma star 1s. Now, I told you like this, that the energy out here is decreasing by delta. The energy out here is increasing by delta. From what? From the energies of the individual atoms. That means also I can say like this, that as the energy is decreasing, it has to be bonding. As the energy is increasing, this is anti-bonding. So I call this as bonding orbital. I'm just repeating whatever I've said about it, just for your clarity. Anti-bonding. Right. Now, hydrogen have got one electron out here. This hydrogen also have got one electron out here. Now the same laws actually holds for filling up of molecular orbitals, just like atomic orbitals. What are the laws? The law says, first of all, is Aufbau principle. What is Aufbau principle? That the orbitals are going to get filled up according to the lowest energy, and then it will go higher to higher energy. What is the second law? The second law is the Hund's rule. What does the Hund's rule actually say? maximum multiplicity. That means if they have got degenerate orbitals, they are first going to basically go into in single spins, and then only it will go on pairing up. So that Hund's rule is also applicable. The third one is called as the Pauli exclusion principle. What does Pauli exclusion principle says? The Pauli exclusion principle says that no two electrons can have all the four quantum numbers same. That means each orbital can have a maximum of 2 electrons, just like what we did in our electronic configuration for atoms. So all the laws for electronic configuration of atoms also holds for molecular orbitals. This is the point that I was trying to make. So I have got 1 electron of hydrogen out here, 1 electron of hydrogen out here. Auber principle लगा दो, एक इलेक्ट्रॉन यहां पर घुसा दो, lower energy. Maximum this orbital can hold actually 2 electrons. 2 electrons hold कर दिया, 2 electron हो गया. Well, how much energy has decreased? For 1 electron, this particular orbitals have come down by delta. I've got 2 electrons now. So the total energy that have decreased is 2 delta. And this is what is called as stabilization energy. Stabilization energy. Try to understand this thing, because based on this only, there will be a lot of questions. 2 delta is stabilization energy. That means when this atom and this atom have combined through linear combination of its atomic orbital with this atomic orbital, they have formed a bonding orbital and an anti-bonding orbital. And following the Aufbau principle, I have put both the electrons at the bottom. And when I put both the electrons at the bottom, we see that my total energy has decreased to delta from what it would have been had it been individual. There's no combination. So the stabilization, the molecule has been stabilized by 2 delta. Energy has decreased. They are happy with the maximum electron density between this atom and this atom. Everything is perfect. Bonding is there. So what is the conclusion? We can say H2 exists. So H2 actually exists. The next part. Suppose I take, instead of helium, instead of hydrogen, suppose I now take helium. Suppose now I take helium. Suppose I now take helium. So I have got helium molecule out here, helium, right? This is my atom A, atom 1. It has got 2 electrons. And which orbital? 1s. I take the second atom out here of helium. Once again, this is my atom 2. And I have got 2 electrons out here. Now, in which orbital it is there? It is also in 1s. Helium का configurations क्या होता है? He is equal to 1s2 होता है ना? So 1s, 2 electrons in 1s. So this 1s and this 1s of this 1s of atom 1 combines with this 1s with atom 2 to form 2 different bonds. One is bonding, the other one is anti-bonding. So this has now become delta. This energy has increased by delta. This is a combination of 1s. So this is my bonding orbital. And I'm going to write down as sigma 1s. This is my anti-bonding orbital. And I'm going to write down as sigma star. Star always means anti-bonding 1s. Sigma 1s. Now I am going to fill up the electrons. How many electrons do I have out here? I have got 2 electrons out here, and I've got 2 electrons out here. So I have got 4 electrons out here. Okay, fine. Let's apply Aufbau principle. 1, 2, 1, 2. So 4 electrons have been reached. Now let me calculate the total energy change when I have all these 4 electrons are there. As far as these 2 electrons are concerned, for each of the electrons, delta amount of energy has decreased. So the total energy decreased is minus 2 delta for these 2 electrons. For the other 2 electrons, say for example, these 2 electrons, what happens is this: for each of the electrons, the total energy has increased by delta. So the total energy is plus 2 delta. I'm calling this as delta 0. Anyway, doesn't matter. Delta 0. So the total energy change is 0. That means by forming or linearly combining helium-2 1s orbitals, there is no gain in energy. There is no loss of energy. If the helium has got nothing to gain, why should they form bond? They only form bonds when they are stabilized. Right? This is my Siddharth. This is my Priyanshu. If Siddharth is getting nothing from Priyanshu, either emotionally or something materially, if Priyanshu is getting nothing from Siddharth, either materially or emotionally, why should they form a bond? They will not form a bond. At least something has to be there between them. Some chemistry has to be between them so that they form a bond. If there's nothing, they will never come to this. They will just drift apart. If there's no advantage in the relationship. Similar is the case out there. Nothing is, no energy loss is there, no energy gain is there. Why should they form bonds? They will not form bonds. Therefore, helium-2 do not exist. Will helium exist? Will helium exist? Okay, this is not a purview of molecular orbital theory. Why? Molecular orbital theory deals with molecules. Where is the molecule in single helium? It's just an atom. Of course it exists, but it's a single atom. Single atom cannot be represented by molecular orbital theory. If you have to explain the existence of helium atom, it has to be some other mechanisms, but not through molecular orbital theory. So whenever you see a molecule and they ask whether a particular molecule exists or not, you have to consider molecular orbital theory. If they ask you about the shapes, you have to talk about VAC-PR theory with the help of valence bond theory. If they ask you about the lone pair of electrons, you have to talk in terms of Lewis dot structure. So these are 3 different ways of actually explaining the bonding pattern, Lewis dot structure, the shapes, the angles, the bond lengths, VAC-PR. A molecule exists or not, molecular orbital theory. And that actually encompasses these 3 things in this particular chapter. Of course, there are some other things, sigma bonds and pi bonds, which I think I'm going to do in the next class also. Maybe I'll continue with this all the next class also. I have to continue anyway, it won't be complete today. But did you understand up to this much, all of you, all 4 of you, all 5 of you? Yes or no?
Yes.
Yes, sir.
Yes,
Okay.
sir.
Out of 5, 2 have said yes. The remaining 3 are silent.
Yes, sir.
Priyanshu says third ho gaya. Anjali and Siddharth is remaining silent. Siddharth is not there. Only Anjali is there. Anjali? Yes or no?
Yes, sir.
Okay, fine. Take it. So this is the molecular orbital theory, right? Now what I'm going to do is this. So I've explained many things. Bonding orbital, anti-bonding orbital, right? Linear combination of atoms. The wave, constructive interference, destructive interference. Stabilization energy, And how do you basically find out whether bond formation is there or not? Right. These are the few things that we have done today. How much time we have got? Okay, about 20 minutes more time. Fine. So what I'm going to do in the remaining part is this. I'm going to show you the different combinations of orbitals. So what I've done till now is I've essentially talked in terms of SS combination. Now I'm going to show you the different combinations that is possible, right? And I'm going to have my hand diagrams, because that will be easier for me. So I have got 1s out here, plus, and I have basically mixing another 1s out here, plus. So when we combine together, what kind of orbital you get? Both of them are plus. So this is my one nucleus, this is my second nucleus. So my structure will be like this. I've already shown you this. I'm just basically drawing all the graphs together now. So this is my plus. So this is my bonding orbital. What is my anti-bonding orbital? I have got plus out here. I'm adding with a minus. So when you are combining this, overlapping this particular thing, when you're overlapping this particular portion is going to eat each other. So how will the graph look like? In between, I'll not be having any kind of a thing. So this will be my structure. This will be plus. This will be minus. And my new nucleuses will be at the periphery. Okay. So this will be my antibond. So what I mixed? S plus S. Right. Now let's move into the second one. Sp. Now what I'm going to do is the addition of Sp. So this was my first diagram. Now let me combine S and P. S plus P. Okay. This is my P orbital. I have got plus, minus. And I have got out here plus, I'm going to add with S. So this is my S. Look out here. This plus and this plus are going to add with each other. This is my nucleus and this is my nucleus. So between these two nucleuses, there will be higher concentration of electrons. So how will my molecular orbital look like? This is my nucleus. This is my nucleus. So in between, I'll be having higher concentration of electrons. So higher concentration of electrons I'll be having. Plus, plus, and out here I'll be having minus. So this will be plus, this will be minus. These are my two nucleus. So between the two nucleus, the highest concentration is there. So you call this as, once again, bonding. Whenever these two pluses are actually in the same side, they'll be bonding. Now say for example, I have got like this. I have got minus out here, plus out here, and I have got basically adding this plus. Right? How will the structure look like? Okay, plus and minus as now, this is my nucleus, this is my nucleus. So plus and minus are going to eat each other. So in between this, so this is my this, so in between these two, there will be no electrons at all. There will be no electrons at all. So how is the structure going to look like? The structure is going to look like is like this. It is going to eat a portion of it. This is going to eat a portion of this. So this will be my plus. This will be my minus, because S and P are of different sizes. So this is not be able to eat completely this. And neither this is be able to completely eat this. So a little bit of minus is going to stay out here. So this is my minus, this is my plus. And this is my plus. Plus means this has eaten a lot. So this will be plus. This side will be decreased, this side will remain intact. So this will be my plus. So between this, there is no electron. You call this as anti-bonding. You call this as sigma S, depending upon 1s or 2s or 3s. So sigma ns kar diya maine, sigma star ns. This is also head-to-head collisions. That means once again sigma bond. So sigma, I'm going to call this as sp. This I am going to call sigma star sp, like this, because I've combined one s with one p. Right? Then comes the next part. So I've combined SS, SP. Now say for example, PP addition. Now what I'm going to do is PP. P and P. Linear combination of PP orbital. कभी कभी देता है exam में ये diagram sir. Just try to understand this. Look at the logic in which I'm drawing this diagram. If you can understand the logic, it will be just like a cake for all of you. Just to draw this diagram at the examination hall. So I have got this. So this is my nucleus, P plus minus. You remember the P orbital, one is plus, the other one is minus. You are going to add this. This is my nucleus. So plus minus. So look out here, you have got plus in this side, plus in this side. So they're going to add up. This is my nucleus, this is my nucleus. So in between this nucleus, there will be maximum concentration. Chalo, kar lo. So this will be my plus. दोनों एक साथ में मिल गया. This will be minus. This will be my minus. So this is a PP. This is a head-on collision. So sigma PP orbital. Now, say for example, I have got the same structure now. Plus, minus. However, in this case, I have got minus out here, plus out here. So what they are going to do, they are going to eat each other a lot. So what will the structure look like? You have got minus, so this is my plus, this is my nucleus, this is my second nucleus, plus and minus. Anyway, a small portion is going to remaining. The minus sign is going to remain intact. This is my plus. Similarly, this minus sign is going to remain a little bit. This will be my plus. So this is what? Once again, head-to-head collision. That means it's a sigma bond, but it's anti-bonding. So sigma star PP, like this. Then I've got, say, for example, the final one diagram I have got is like, the final diagram is like this. I'll got another kind of PP bond. This was my sigma bond. Because all of them, in case this a headed collision, is sigma bond. Headed overlap is taking place. Sigma bond. Whenever headed overlap is taking place, it is called as sigma. But look now out here, PP. But out here, it will be pi bond because of lateral overlap. Lateral overlap means what? Suppose I have got this is my axis and I've got a p orbital like this, plus, minus. And this is my first nucleus, this is my second nucleus. And I've got another p orbital like this, plus and minus. Now, I'm bringing this towards it and this one towards it. Now there is no longer a headed overlap. Instead, there's a lateral overlap. Lateral overlap is in this direction. No direct overlap, lateral overlap. So how will the structure look like? So plus, plus in the same side, minus, minus in the same side. So you have got a nucleus out here, you've got nucleus out here. Plus, minus. So it was the same sign together, they're coming out. So you will call this as pi PP or pi orbital. It's a pi orbital because lateral overlap is taking place. Whenever lateral overlap of orbitals takes place, you call this as pi orbitals. Now look at the other one. I have got plus out here, minus out here. I have got minus out here, plus out here. Now what is going to happen? This is going to eat a portion of this. This is going to eat a portion of this. This is going to eat a portion of this. This is going to eat a portion of it. So how will the structure look like? यहाँ पर तो पूरा खत्म हो जाएगा, यहाँ पर भी पूरा खत्म हो जाएगा. I have got plus, minus, this is my one nucleus, minus, plus. You call this as pi star orbital. This is my bonding. This is my anti-bonding. Simple. एबार practice करके देखो. Practice करके देखो. Siddharth, did you understand better? Your net is creating a lot of problem today. Siddharth? Anjali, did you understand? Anjali?
हाँ सर.
Priya Shah? Priyanshu?
Yes sir.
Priya Srivastav?
Yes, sir.
Priyanshu?
Yes, sir.
एक बार प्रैक्टिस करके देखो. एक तो कॉम्बिनेशन करके देखो. होता क्या देख लो. Then you'll understand why you are getting stuck and ask me. After this is over, I'm going to write down the electronic configuration. Chalo. Any problem? Priyanshu, is okay? The diagrams? You have understood how to draw the diagrams,
Yes,
Priyanshu? You have understood how to draw the
Yes,
diagram?
sir.
Riya? Srivastav?
Yes, sir.
You have understood how to draw the diagrams? Could you practice
Yes,
a little?
sir.
Because sometimes they ask you what will be the diagram of PP direct overlap, sigma bonds. Riya Shaw, you have understood how to draw the diagrams?
Yes, sir.
Anjali, Siddharth?
Yes, sir.
Siddharth? This microphone is not working, it seems. Chalo. Now, what I'm going to do is I'm going to write down the electronic configuration. I'm going to write down the electronic configurations now. Now, tell me this. Not much is required. Not much is required. In this is not much is required. We are going to talk about the applications next class. But first of all, let me tell you this. Suppose my energy increases in this way. Suppose my energy increases in this way, right? The first orbital, atomic orbital, which has got lowest energy is 1s. So when two 1s combines, the energy will be the lowest. Next one is 2s. I'm just writing down the Bohr-Bury law, N plus L law. How can you find out the energies of two orbitals? I'm doing the same thing. So 1 is 2s. Then comes 2p. In 2p, I have got three orbitals. So if two 2p's actually mix, I'll be having 6 orbitals. I require for molecular orbital only up to this much. Right. So when 1s plus 1s combines, the energy will be minimum. Then comes 2s plus 2s. Then comes 2p plus 2p. By the way, I've forgotten one thing to mention, which is supposed to be it's supposed to be implicit. I have basically actually mixed up two atomic orbitals. Mixed two atomic orbitals. One atomic orbital was this, the other one atomic orbital was this. So mixing two atomic orbitals gives you how many molecular orbitals? Gives you 2 molecular orbitals. Two molecular orbitals. So when you mix two atomic orbitals, you will get 2 molecular orbitals. So that means what I'm trying to say is this. That when you are mixing 1s orbitals, two 1s orbitals, you'll be getting 2 molecular orbitals. When you are mixing two 2s orbitals, you'll get 2 molecular orbitals. Now out here, there are 3p orbitals. So if you are mixing 6p orbitals, 3 from this atom and 3 from the other atom, you'll be getting 6 molecular orbitals. Right? So let me draw the diagram. This diagram people don't understand, but it's very simple to understand. So this is how my energy actually goes on increasing in this way. What I'm going to do is this. I'm first going to mix 1s orbital out here. This is my energy, right? In this direction, it is increasing. So I have got 1s orbital. For one atom A, this is my atom A. And this is my atom B. So I have got 1s orbital out here. So two 1s orbitals of one from atom A and one from atom B is mixing. So I'll be getting 2 molecular orbitals. One is this. The other one is this. Right? So I call this sigma 1s and I call this as sigma star 1s. Then I have got 2s out here. I have got 2s out here. See, for atom A and atom B. So 2s of atom A and 2s of atom B. So I'll be having once again 2 orbitals. So this will be my sigma 2s. This will be my sigma star 2s. Then I have got, this is interesting, then I have got 3p orbitals of atom A. And I'm combining with 3p orbitals of atom B. I'll be having total 6 now atomic orbitals. And how will these atomic orbitals actually be staying? First of all, what I'm going to have is this. I'll be having out here sigma I'll be having this. I'm basically mixing 2p. And out of this 2p, I have got 2px, 2py, 2pz. Similarly, I've got out here 2px, 2py, 2pz. So if I say that 2px orbitals are going for sigma p orbital, then I'll be calling this as sigma 2px. Then I'll be having 2p orbitals. Look, this pp overlap is taking place. That means 2 pi orbitals I'll be having. So it will be like this. Like this. So this will be pi 2py and pi 2pz. Right? Now, out here, I'll be having 2 more orbitals. This will be called as pi star 2py and pi star 2pz. And then this sigma 2px was minimum, so out here sigma 2px will be maximum. So this will be sigma star 2px. This is my electronic configurations. Now the same rules, Auber principle, Hund's rule, Pauli exclusion principles, all says what? Electrons has to be filled from the lowest energy. Maximum multiplicity, that means where degenerate orbitals are there. What do you mean by degenerate orbitals? By degenerate orbitals, we mean that essentially the orbitals having the same energy. In their maximum spin multiplicity will be there. That means the Hund's rule. Pauli exclusion principle says this what? That no 2 electrons will be having all the 4 quantum numbers same. That means maximum I'll be having 2 electrons per orbital. That means this was my pictorial diagram. If I want to write it down in terms of electronic configuration, I can simply write this as, I can simply write the electronic configuration as sigma 1s, minimum energy, sigma star 1s, sigma 2s, so I have completed this too. This is my energy curve. Sigma 2s, sigma star 2s. Then I have got sigma 2px. Then I have got this pi orbitals. Let me put it out here. Both of them are same energy, so I'm writing down in the same club, pi 2py, pi 2pz. Then I've got this pi star 2py, pi star 2pz. Then I have got sigma star 2px. So this is my electronic configuration. Right? Now, there are 2 laws out here. This law, when this sigma 2px is out here, but in this order, this electronic configuration is only for oxygen and above. Now, an atomic number of oxygen and above. Only for this particular actually holds. But if you go for, say, for example, below oxygen, that is lighter elements. Then what happens is this, only this one changes its position and goes out here. That means the electronic configuration for this will be sigma 1s, sigma star 2s. You have to remember this actually, sigma star 1s, sorry. Then sigma 2s, sigma star 2s. Then this is going to shift in between. So out here, I'll be having this one now. Pi 2py, pi 2pz. Then I'll be having this sigma 2px. And then I'll be having pi star 2py, pi star 2pz. And then I'll be having sigma star 2px. Only this one has changed the position. Otherwise, everything is the same. But you have to remember this because this question often comes. Write down the electronic configuration of the molecule. So this is the electronic configuration, but all you have to remember is this. This is below oxygen. Sorry. This will be applicable for below oxygen. This will be for below oxygen. This electronic configuration. But for oxygen and above, below oxygen means oxygen not included. Mind it. For this, oxygen is not included. This electron, oxygen not included. For this, oxygen and fluorine included. Oxygen is included. Now I'll give you an example how to write down the configuration. Say for example, I want to do it for nitrogen, right? Say I want to do for nitrogen molecule, no longer atom. We are talking about molecular orbitals means you have to consider molecules only. That means say for example, I want to basically consider nitrogen. Very good. That means it is below oxygen, atomic number, lighter elements. That means I have to take this particular configuration below oxygen. I have to take for this particular electronic configuration. So let me write it down. क्या होगा? So nitrogen. Look out here. What I'm going to do. No longer valence electrons. For Lewis dot structure, you did valence electron. For hybridization, you did valence electrons. For VSEPR theory, you did valence electrons. But out here, mind it, write down in your notebooks, in all caps, that for this, you have to take the total number of electrons. That means for nitrogen, I'm combining 2 nitrogens. So each nitrogen has got 7 electrons. So 7 plus 7 is equal to 14 electrons. No longer valence electrons. You are now going to take the total number of electrons. It's a lighter element. And it is lighter element. So what will be the electronic configuration out here for the molecule? Sigma, see how I write it down. Sigma 1s2. I'm going to use this, sigma. Sigma 1s is one molecular orbital, and each molecular orbital can hold 2 electrons. So what I have done this is a sigma bond formed between the overlap of 2 1s orbitals, and the molecular orbital has 2 electrons. This is the meaning of this thing. So when I'm writing this, say for example, sigma, it means it is sigma bond or sigma overlap. 1s means combination of which orbitals? And 2 means number of electrons. This is how you write down the configuration of it. Same. Out there in atomic cases, you written 1s2. It's an electronic configuration. So it was just 1s. And this is 1 orbital, 2 electrons. 1s2 you have written down out here. But out here, since a molecule is getting formed, and there are 2 kinds of bonds, sigma and pi, therefore you need to designate the bonding also. So it's a sigma bond is formation. But it is direct overlap is there. Combination, this molecular orbital is formed by overlap of 2 1s orbitals. So sigma 1s. How many electrons? 2 electrons. So that's how you write it down. So this will be sigma 1s2. Then comes sigma star 1s2. That is the anti-bonding. That means essentially this orbital. So first you have got these 2 orbitals filled up. Then you have got these 2 orbitals filled up. So that's why I write down sigma 1s2. Therefore, the next one is sigma 2s2. What you did was this, sigma 2s2. Output principle, lowest energy to higher energy. Then sigma star 2s2. I've got 14 electrons. Right now I've taken care 2, 4, 6, 8. So another 6 to go. Now basically I've got up to this much. Then comes sigma 2px, 2 electrons. So I'm going to write down sigma. By the way, it's a lighter element. Lighter elements means 2px will be out here. So sigma 2px will not be there. Out here will be pi 2py. So I'm going to write down. So I'm going to write down pi with a bracket like this. What does this bracket means? That both of them are same energy. So 2py pi 2pz. Right? So degenerate means Pauli exclusion principle 1, 2, plus then after both of them have filled up, that means out here and out here, then pairing is going to start. So pi 2py2, pi 2pz2. So pi 2py2, pi 2pz2. So 2, 4, 6, 8, 10, 12. Another 2 to go. So which one would be for lighter element? Sigma 2px. Sigma 2px2. So see how many? 2, 4, 6, 8, 10, 12, 14. Done. This is the electronic configuration. Same way. All you need to understand is this. All you need to understand is this diagram. That's it. And then you have to remember this sequence. Important is this one. You have to remember this and you have to remember this. And with this, you will be able to solve majority of the problems in molecular orbital theory. And you can be damn sure that some questions, whatever board you belong to, will surely come either from molecular orbital theory. There are a few more things out here. Show oxygen is paramagnetic, whether the molecules are going to exist or not. So what are the few things that you need to do? What are the few things you need to do? Number one is, what kind of questions you can expect out here? Whether a molecule exists or not. I've explained with helium. This is the first kind of question you can answer. Second question is magnetic behavior. These are something which you are going to do in the next class in details. Magnetic behavior. The third thing that usually comes is bond order. So all these three things we are going to do in the next day. So I think we have done a lot today. Let me ask you if anybody has got any questions. Priyanshu, अभी तक clear है बेटा?
Yes, sir.
How was your vacation? At your home? Muzaffarpur? Not Muzaffarpur. कहाँ बोले थे? Near Haridwar?
Saharanpur.
Taran. How was it? Good?
Yes, sir. Yes, sir.
What
Sir,
kind
I
of
am there
mithai?
only.
You are there only. So you are
Yes.
getting good. You are getting treated well. Different kinds of foods every day.
Yes, sir.
Oh,
Yes, sir.
so bring us some. Bring for us something. Eat yourself alone.
Okay.
When?
Sir,
रिया श्रीवास्तव
when will you meet up?
ये तो जिंदगी में नहीं होगा बेटा. चलो रिया श्रीवास्तव.
Yes, sir.
Did you understand better today?
Yes, sir.
Any problems? Any issues?
No, sir.
Riya, you are pretty irregular, better.
हाँ sir.
You are pretty irregular.
सर वो कुछ दिन से तबीयत ठीक नहीं था सर. वो चालू है.
लास्ट दिन को नहीं बोल रहा है, कभी कभी बोल रहा है. या ठीक है, चलो. रिया शाह, any questions better?
No, sir.
एकदम पूरा क्लियर.
हाँ, sir.
अंजलि, पेंटिंग ओवर एट योर होम.
हाँ सर, कब का खत्म हो गया.
बुक्स भी पेंट कर दिया ना, पूरा व्हाइट बना दिया ना, कोई पढ़ नहीं पा रहे
सर
हो.
क्यों बुक पेंट करेंगे हम.
एकदम कोई पढ़ना नहीं होगा, पूरा व्हाइट कर दिया एकदम पूरा.
नहीं सर, ऐसा नहीं किए.
आज पूरा क्लियर है बेटा.
सर आप वीडियो भेज दीजिएगा ना, मतलब एक बार देखेंगे. मतलब
हाँ, भेज देंगे. वो तो एक कल भेज देंगे.
ओके सर, भेज दीजिएगा.
ठीक ठीक सिद्धार्थ any questions बेटा your microphone is not working अरे
No,
microphone work
no,
करना
sir.
एकदम पूरा clear
Yes, sir.
where are you right now Delhi or basically you are still at Himachal Pradesh
Delhi, sir, Gurugram.
आ गया घर में
Yes, sir.
what did you do in Diwali
Yes, sir.
what did you do in Diwali at your home
सर जो होता है दिवाली पे
क्या होता है पटाखा हुआ
हाँ सर हुआ पर मैंने नहीं करा
कैसी हुआ बेटा तो गवर्नमेंट ने बैन कर दिया था ना
नहीं सर उधर नहीं है
कहाँ पर हिमाचल प्रदेश में कहाँ पर रह गए थे अपने
ये सर उन्ना डिस्ट्रिक्ट है
कौन सा
उन्ना यूएनए
ऊना में
यस सर
that is in plains then that not in hills
नहीं सर है थोड़े बहुत है
तो थोड़े बहुत it's just the beginning of the hills I guess
यस सर
ऊना गया है मैंने ठीक है चलो बाय
बस
थैंक यू सर
Thursday
बाय सर गुड नाइट सर
अच्छा
बाय सर
bye Riya Srivastava
यस सर
we shifted the time for you at 2:15 and in 2:15 you vanished
नो सर आई विल जॉइन
ठीक है चलो बाय 2:15 on Thursday
ओके सर बाय
okay bye चलो जा
হ্যাঁ বন্ধ করো কথা বলছি